Now in the last video, we have seen that when light travels from a rarer medium to a denser medium, that bends towards the normal. Now here we have angle of incidence in this case greater than the angle of refraction, and angle of incidence is equals to angle R plus angle del. Now this angle I, this is equals to angle R plus angle del, because this angle and this angle, they are vertically opposite angle, they must be equal to each other. So I is equals to R plus del. So from here you get angle I is equals to R plus del, and you get del, that is angle of deviation, as I minus R. This is the first case. Now we move on to the second one. The second case is like this: when light travels from a denser to a rarer medium, that bends away from the normal. So here you have a denser medium and a rarer medium, and this is the surface separating two different media. Denser medium I have taken as water, and rarer medium I have taken as air. So let's say the light is incident like this, obliquely, on the surface separating two different media. Again I will name it as AO, and here you have a normal. This is the normal. Now you know this is the angle of incidence, angle between incident ray and normal. I'll name the normal as N dash. You also know that suppose if we have a single medium only, then the light would have traveled in the straight line path like this. Now here light, instead of bending towards the normal, as it is moving from denser medium to rarer medium, it bends away from the normal like this. It goes like this. So here also you have OB as the angle of refraction. This OB is the refracted ray, and this angle is the angle of refraction. So here also you have a partial amount of reflection. So light is partially reflected also. I'll name it as OC like in the previous case. And this angle is denoted by capital R, which is the angle of reflection. Now this angle, the angle between the incident ray produced forward and the refracted ray, this angle is called angle delta. Now you can clearly see that in this case, if you see it clearly, this angle I is smaller than angle R. This angle and this angle, they are vertically opposite angle. So therefore, in this case, angle delta will be equals to angle R minus angle I. So this angle and this angle, they are vertically opposite angle. If this is I, this will also be I. So del will be equals to R minus I. Now we are moving on to the third case. Third case is that when the light is incident normally or perpendicularly on the surface separating two different media, then it travels undeviated, or no bending of light or refraction of light takes place. So here you have surface separating two different media, medium 1 and medium 2. I can take any medium 1, medium 2 I have taken. So suppose say if the light is incident like this, normally, the light is incident normally, then light passes without any deviation, goes out straight. That means there is no bending of light, no refraction of light. So here angle of incidence will be 0 degree, angle of refraction is also 0 degree, and angle of deviation, as there is no bending of light, this is also 0 degree. This is one of the important conditions. Although here light is traveling from one medium to another medium, when light travels from one medium to another medium, the speed of light also changes. But as the light is incident normally, perpendicularly, then here no refraction takes place. So if you measure the angle of incidence means the angle between the incident ray and the normal. Angle of incidence is 0 degree, because the same line is the incident ray, same line is the normal. So angle between them is 0 degree. Similarly, angle of refraction is also 0 degree, because this is the refracted ray and the same line is the normal. And since there is no bending, so angle of deviation is 0 degree. So these are the three cases you need to understand. Now we are moving on to the laws of refraction of light. The first law says that the incident ray, the refracted ray and the normal at the point of incidence, all of them lie in the same plane. So here you can see clearly, this is your incident ray, this is your refracted ray, and this is your normal. All of them are lying in the same plane. Okay, so first law says that the incident ray, the refracted ray and the normal at the point of incidence all lie in the same plane. Now the second law, which is also called the Snell's law, it says that the ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for a pair of media concerned. This law is important. So this constant is called the refractive index of second medium with respect to first medium. So you can say ratio means numerator by denominator. So ratio of sine of angle of incidence to the sine of angle of refraction is a constant, and this constant is called refractive index of second medium with respect to first medium. Refractive index of second medium with respect to first medium. Refractive index, it can be denoted by small n or letter mu. It can be denoted by mu also. So these are the two laws of refraction of light. Now we'll be moving on to the refractive index. Refractive index is also called index of refraction, or you can say power of refraction also. So index of refraction or refractive index of a medium, of an optical medium, is the measure of ability of the medium to bend or refract light. Whichever medium bends the light more is said to have higher value of refractive index. Different media, bends the light by different amount. Whichever medium bends the light more, that medium is said to have higher value of refractive index. Like for example, glass bends the light more than water does. Therefore, refractive index of glass is greater than that of water. Okay, so refractive index of the second medium, refractive index you can define like this also. Refractive index of the second medium with respect to first medium is defined as the ratio of the speed of light in the first medium to the speed of light in the second medium. Refractive index of second medium with respect to first medium. Refractive index of second medium with respect to first medium, this is equals to refractive index of speed of light in the first medium, we have denoted by B1, divided by the speed of light in the second medium, we have divided by B2, denoted by B2. So 1 mu2 is B1 by B2. So this is B means speed of light, this B2 also means speed of light. So its unit is meter per second, its unit is also meter per second. So units get cancelled, so you get a pure number. So that is why refractive index is a pure ratio. Absolute, we have two types of refractive indices. One is called absolute refractive index and the other one is called relative refractive index. Whatever definition we have written here, this is the definition of relative refractive index. Suppose say if the first medium be air or vacuum, then the refractive index of second medium with respect to first medium will be called as absolute refractive index. So absolute refractive index of a medium is defined as refractive index of medium with respect to air or refractive index of medium with respect to vacuum. That is the absolute refractive index. It is defined as the ratio of the speed of light in air or vacuum, the speed of light in that medium. So if I have given one example, absolute refractive index of glass, that is refractive index of glass with respect to air or refractive index of glass with respect to vacuum. This is given by this definition, speed of light in air or vacuum, which is equals to 3 into 10 to the power meter per second, and the speed of light in that medium here is glass, so speed of light in glass is 2 into 10 to the power 8 meter per second. Meter per second get cancelled, 10 to the power 8 and 10 to the power 8 also get cancelled, so 3 by 2 you'll get as 1.5. So absolute refractive index of glass or the refractive index of glass with respect to air is 1.5. So similarly, We can also find the refractive index of glass with respect to water. So refractive index of glass with respect to water, it is written like this. So this is, by definition, this is equal to speed of light in the first medium to the speed of light in the second medium. First medium is water, so speed of light in water is this much, 2.25 into 10 to the power 8 meter per second, and speed of light in the second medium is glass, so speed of light in glass is 2 into 10 to the power 8 meter per second. So they get cancelled, so ultimately you are getting like this. So in this manner you can find refractive indices of the different media if you know the speed of light in different media. So one more thing you need to know, that this refractive index depends on several factors. First factor is that it depends on the nature of the medium, because in different media the speed of light is different. When the speed of light is different, the refractive index is also different, because refractive index depends on the speed of light. It depends on the speed of light. It also depends on the color of the light used. Like for refractive index of glass, for red color is different, and for violet color it is different. So it also depends on the color of the light used, color or the wavelength of light, you can say. Now the next one is, we have conditions for no refraction of light. There are two conditions when no refraction takes place. First condition we have already discussed. First condition says that when light travels normally, when light is incident normally or perpendicularly on the surface separating two different media, then light travels undeviated, or no refraction or no bending of light takes place. If the light is incident normally, then no refraction takes place. This condition we have already discussed here. This is the condition when no refraction takes place. Here, although you have two different media, but the light is incident normally, so that is why no refraction is taking place. The second condition is, when the refractive index of second medium is equal to the refractive index of the first medium, then no refraction or bending of light takes place. Like here, I have taken two different media. This is the surface separating two different media. So absolute refractive index of first medium is also 1.5. Second medium is also 1.5. So if the light is incident obliquely also in this case, then no refraction takes place. Light goes straight without bending. So these are the two conditions for no refraction, when no refraction takes place. Now next one we have is the principle of reversibility of light. According to this principle, the path of the light ray is exactly reversible. Path of the light ray is exactly reversible. We have medium 1 and medium 2, and here this is this surface separating two different media. So below this surface there is second medium, above this surface there is first medium. So this is the incident ray AO, this is the normal angle of incidence. So light, as it travels from one medium to another medium, it is bending towards the normal, which indicates, from the diagram it is understood that second medium is denser than the first medium. That is why the light is bending towards the normal. Light is traveling from rarer to denser medium, it is bending towards the normal. This is angle of refraction. So here, when light is moving from first medium to second medium, if we apply Snell's law, then for light traveling from first medium to second medium, medium 1 to medium 2, by Snell's law you get sine of angle of incidence to the sine of angle of refraction. This is equals to refractive index of second medium with respect to first medium. So let's say this is equation number 1. Suppose now initially light has followed this path A, O, B. Suppose at this point, if we place a plane mirror, and if this light ray OB is made to fall on the plane mirror normally or perpendicularly, then what will happen? After being incident on the plane mirror, it rebounds following the same path. It returns like this. Now this light, you can say BO, once it reaches here, it is traveling from medium 2 to medium 1. So now it is moving from, this light is moving from denser medium to rarer medium, so it will bend away from the normal. So it goes like this now. It goes like this. So in the second case, after reflection from this plane mirror, this BO is your incident ray and OA is your refracted ray now. BO is incident ray and OA is your refracted ray. So if you apply Snell's law here, for light ray traveling from medium 2 to medium 1, by Snell's law, you get sign of angle of incidence. So angle of incidence in the second case is R, because in the second case, OB is the incident ray. So angle between incident ray and normal is called angle of incidence, divided by the sign of angle of refraction. So in the second case, OA is the refracted ray. Angle between refracted ray and the normal is called angle of refraction. So angle of refraction, here it is denoted by I. So you get it like this. So angle sin R by sin I is equals to refractive index of second medium with respect to first medium. So when light travels like this from B to A, so second medium is 1, medium 1, and first medium is medium 2. So here it becomes like this. Refractive index of second medium, which is medium 1, with respect to the first medium, which is medium 2. So let's say this is equation 2. So here you have equation number 1 and 2. If we multiply these two equations, it gives, so if you multiply this one and this one, so you get like, you can write like this, equals to, then you have to multiply the left hand side also. So if you multiply these two, then sin I and sin I gets cancelled, sin R and sin R also gets cancelled, so you get 1. So you are getting 1 mu 2 into 2 mu 1 is equals to 1, which gives you 1 mu 2 is equals to 1 by 2 mu 1. This is important result. Okay, so with the help of this result, this expression, we can calculate, we can find the value of refractive index like this also. Suppose say, for example, if we have refractive index of glass with respect to water is equals to 9 by 8. We already know this value. We have already calculated this value. We know this value. Now if you are asked to find refractive index of glass with respect to water, then how to proceed? By applying the same formula. So we know refractive index of water with respect to glass. You can write like this. Here you have 1 mu 2. It can be written as 1 divided by 2 mu 1. So here if we apply the same principle here, G mu W, this will is equal to 1 divided by W mu G, following the same principle. So you know the value of this one. Refractive index of glass with respect to water, it is already given here. Write the value here. So this is, long line is a division. So if you reciprocal it, you will get 8 by 9. So these things, this type of problems also you need to know. Now the next thing is the refraction of light. Refraction of light through a rectangular glass block or a parallel glass block. This can be called as rectangular parallelepiped. This rectangular glass block I marked this as P, Q, R and S. This is rectangular glass block. So here this AB is the incident ray. This is the normal drawn here. Light is moving from air to glass. So from rarer medium to denser medium. So definitely it will bend. So it bends in this direction. So you get the refracted ray as BC. So again, once the light reaches here, for the surface, for the second surface SR, this BC is the incident ray. So here light is moving from denser medium to rarer medium, glass to air. Again here refraction takes place. So since the light is moving from denser to rarer medium, it bends not towards the normal but away from the normal. It comes out like this. If you produce the incident ray in the forward direction, it comes out like this. That means if there is no glass block, only air is there, then light would have traveled following this path, straight line path. But since refraction takes place here 2 times in the glass block, so light comes out like this as CD. So CD is your emergent ray. So I is angle of incidence, this is angle of refraction R. If this angle is R, this will also be R. This type of angles are called alternate angles. and here this is angle of emergence, angle between emergent ray and normal. This is called angle of emergence. So whenever refraction takes place through a parallel glass block, then bending of light does not take place. That means its direction of the path of light does not change. Initially light was going in the same direction like this. After refraction, 2 times refraction also, it is going in the same direction. So there is no change in the path of the light. But instead of going from here, light comes out like this. That means it is laterally displaced. It is laterally displaced. If you measure this perpendicular distance between the incident ray produced forward and the emergent ray, this perpendicular distance is called lateral displacement. So whenever refraction takes place, whenever light passes through a parallel glass block, although refraction takes place at 2 surfaces like this, here also, but there is no change in the path of light. The angle of deviation is 0. But you need to know that angle I and angle E, angle of incidence and the angle of emergence, they become equal to each other. And this perpendicular distance between the incident ray produced forward and the emergent ray, this is called lateral displacement. I have given you the definition of lateral displacement also. The perpendicular distance between the incident ray produced forward and the emergent ray is called lateral displacement. Now this lateral displacement, whether it will be small or big, it depends on many factors, but I have given you 2 factors here. One factor is angle of incidence. If this angle of incidence is less, lateral displacement, the value of this distance will also be less. If it is more, this lateral displacement will also be more. It also depends on the thickness of the glass block. Thicker the glass block, if the glass block is thicker, then lateral displacement will be more. If it is thin, lateral displacement will be less. So I have given you only 2 factors. First one is the angle of incidence. So lateral displacement increases with the increase in the angle of incidence. And the second factor is the thickness of the glass block. Thicker the glass block, more will be the lateral displacement. Now the next topic is formation of multiple images in a thick glass plate or a thick mirror. You must have noticed this. Whenever you see a thick mirror, then in that case, instead of seeing one image, you see multiple images. Like for example, when an object such as a candle or a pin or anything placed in front of a thick mirror or a thick glass plate is viewed obliquely, then multiple images are of the object are seen. So instead of seeing just one image for the object, you see many images. So out of these images, the second image will be the brightest. Why the second image will be the brightest? Because the maximum intensity of light is concentrated on it. So in order to explain this, I have drawn the diagram also. So let's say this P, Q, R and S. This is a thick mirror, and this surface RS or SR of this surface is silvered. This surface is silvered. Back surface of the mirror is silvered and coated with red oxide. So this is this surface. So here you have the object O. It may be a candle, it may be a pin, anything. So from this object I have taken 2 incident rays, 2 rays of light. One ray is coming like this. It is incident normally on the surface PQ. So it passes without any deviation. So from here, silvered surface light cannot pass. So that is why it is reflected back. So it goes like this. Another ray I have taken like this. This is incident not normally like in this case, but it is incident obliquely. So here reflection takes place, partial amount of reflection, and majority of light is refracted. So in order to understand this, so I'll explain you this with the numbers. Like for example, let's say here you have 100% of incident light coming in. Out of the 100% of incident light coming in, let's say for example, if 10% of the light is reflected back, then 90% of light will go in. Because whenever refraction takes place, only partial amount of light is reflected. Majority of light is refracted. So now beyond this, light cannot pass. So let's say out of 90, let's say 90% of light is reflected back. In fact, some part of the light will be observed, but I'll take it as 90 only. So this light, as it goes like this, so again here, it is moving from denser medium to rarer medium, glass to air. So it will bend away from the normal. So that means majority of light out of, let's say 90, majority of light 80 will be refracted, and let's say about 10% is reflected back. So again here reflection takes place. Here light comes, 10% of light comes here and gets reflected. So 10 goes back, and again here refraction takes place. So since light is moving from denser to rarer medium, it bends away from the normal. So let's say out of 10, let's say for example, majority of light is refracted. Let's say for example 8 out of 10, 8% is refracted, and let's say only 2% is reflected. So this process will continue. So person seeing from here will see multiple images. This person will see these rays of light. To him, these rays of light appears to come from these points, produce backward here, these points, produce backward, this is also produced backward. So he will see, the person will see the number of images. You have only one object, but you are seeing the number of images. I can keep on drawing this. So you will see multiple images, infinite number of images. So out of these images, I1, I2, I3, I4, I5, and so on, the second image will be the brightest. You can clearly see this second image. This is here in the second image, maximum intensity of light is concentrated. So that is why the second image will be the brightest.